Welcome back to our heat transfer class, where we're delving deeper into the one-dimensional, steady-state heat conduction. This video was made with the support of InnoEnergy. The topic of one-dimensional steady-state conduction is divided in several lessons. There is at least one video for each lesson. Let's continue with the 10th one. This video explains the resolution of two exercises. Let's start with a single fin of adiabatic tip. Regarding the fin, the rod diameter, its length, and its thermal conductivity are given in the table. Also in the table, you can find the boundary conditions, that is, the base temperature, the fluid temperature, and convection coefficient. We are asked to calculate temperatures and heat transfer rates at different points. We will start calculating some parameters. Since the fin is a cylinder, its perimeter is pi times the diameter, and the cross-sectional area is that of a circle. The buoyant number is so small that the one-dimensional conduction can be assumed with a very little error. Because the fin tip is adiabatic, the fin area is the perimeter times the length. The M parameter of the fin is small, around 7. However, because the length is high, the efficiency is low for what is expected for a fin. The temperature distribution for a fin of adiabatic tip can be taken from the literature or obtained from the solution of the differential equation of a fin. The temperature excess for x equal to 0 is 65 degrees. The temperature excess for x equal OT 0.1 is around 38.55. And the temperature, 63.55 Celsius degrees. For the tip of the fin, the expression for calculating the temperature is more simple. With the excess temperature function, theta 0, mf and Lf, we can calculate the excess temperature at any position, and the temperature at any point of the fin. From the temperature distribution, and applying the Fourier's law, we can find the conduction heat transfer rate at any point. For x equal to 0, we have the base heat transfer rate, which is around 13 watts. For x equal to 0.1, the heat transfer rate for conduction through the cross-section is 5.256 watts. And for x equal to Lf, you can check that the heat transfer rate by conduction is 0. The heat released to the fluid by the fin from the base to a given point can be calculated integrating the Newton's law. As you can see in the graphic, for any value of x, the sum of the conduction through the fin cross-section plus the heat dissipated by convection from the base to this point is equal to the conduction heat transfer rate at the base. You can see that these curves are not linear, and the point where conduction equals to convection is below half the fin length. Let's do an exercise with a fin surface. It consists on a heat sink placed between two fluids at different temperature. The left hand is a plane surface in contact with fluid 1. The right hand is a fin surface with 16 fins regularly distributed in contact with fluid 2. Fins are cylinders of diameter df. These fins have a contact resistance in the base. The data for the completion of the exercise are given in the table. In this exercise, we are interested in calculating the heat transfer rate between fluids 1 and 2. For this, we can use the electrical analogy with 3 thermal resistances is series. The thermal resistance for convection in a plane surface, as well as the thermal resistance for conduction throughout a plane wall, are well known. In the theory of fins, we have seen the heat transfer rate of a fin surface. For fins with contact resistance in the base, we must use the efficiency that takes into account this resistance. This efficiency formula was developed in the theory of fins. With all this information, we can build the expression for R2. and the expression for the heat transfer rate between fluid 1 and fluid 2. Now is time for calculating the geometric parameters and the efficiency of fins. After calculating the perimeter of one fin and the cross-sectional area of one fin, we can calculate the Biot number to check the one-dimensional conduction hypothesis. The M parameter is calculated using H2. The area of one fin in contact with the fluid is the perimeter times the length plus the cross-sectional area. The prime area is the cross-section of the plate minus the cross-sectional area of one fin times the number of fins. Now is time to calculate the efficiency with the formula for fins of convective tip. And the efficiency of fins with a thermal resistance in the base. Finally, the heat transfer rate is 14.85 watts. If there were not a contact resistance in the base of the fins, the heat transfer rate will be 15.28. That is, a value almost 3% larger. If fins are removed, the heat transfer rate will be only 5.28 watts. For the values calculated for the fins with contact resistance, we are going now to calculate temperatures and components of the heat transfer rate. Using the convection resistance with fluid 1, T1 can be calculated easily. With the combination of the convection plus conduction resistances, we calculate the temperature of the prime area, T0. Because there is a contact resistance, for calculating the temperature of the base of the fins, we need to calculate first the heat transfer rate at the base of fins, Q0. At this point, we can also calculate the heat transfer rate for the prime area and check the energy conservation at this surface. Because Q0 passes through the contact resistance, it is possible to calculate the temperature of the base of fins, T0*. Using this results, we can calculate the temperature distribution in the plate and in the fins. We first calculate the temperature excess at the base of the fins, after the contact resistance. The MF parameter was already calculated when calculating the efficiency. The temperature profile is the one of a fin of convective tip. The temperature profile in the plate is linear. The temperature difference in the base of the fins is due to the contact resistance. And the temperature in the fins is calculated with the formula. With the same formula, the temperature at the tip can be calculated. We can calculate now how Q0 is distributed between the lateral surface and the tip surface. For the lateral area of the cylinders, we must integrate the Newton law between x equal to 0 and x equal to LF. The theta function for this kind of fins must be used. All the constant terms are placed out of the integral. The integral of the cosine is the sine and the integral of the sine is the cosine. The sine of 0 is 0 and the cosine of 0 is 1. Terms can be rearranged. And the result gives 11.588 watts. It represents a very high percentage of the heat coming from the fin's base. The heat transfer rate at the tips can be calculated using both the Fourier's law or the Newton's law. It represents, in this case, around 3.5% of the heat released to fluid 2. In this example, we have seen how to calculate temperatures and heat transfer rates for a system including a fin surface.